Hi guys, this is MA315. Welcome to the course. My name is Robert von Fay-Siebenburgen and I'm going to be your lecturer. During the lecture course you can contact me either personally, although at the moment this is not really recommended to have face-to-face meetings, so an alternative is then via Blackboard. Another even safer and I think more efficient option is the email. So if you send me an email to robertus@sheffield.ac.uk, I think that's the best, because mostly I hang on email and I will respond very quickly. My office is in H16 in his building, but at the moment, as I said, I don't think this is practical information for you. Now let me introduce you very briefly what the syllabus of MAS315 will be. Excuse me. We will initially study waves. The reason why we study waves is because waves are described by one of the big classes of partial differential equations. It's a hyperbolic differential equation. We will study waves and oscillations on strings, and initially, and we will use a very nice analytical solution developed by D'Alembert about 200 years ago. Then we are going to study propagating waves and standing waves on strings, and we will go into the so-called normal mode analysis. Basically, I'm going to show you here that if you have a general perturbation in a system, for instance in a physical system, and if you study the system linearly, I will define all these terms later, then you can usually find a set of, very often an infinite set of functions, that the superposition of these functions will describe pretty well the actual perturbation of the system. That is called basically the normal mode analysis. Then we will move on and we will study the Fourier series, and we will link how the Fourier series are, we will investigate how the Fourier series are linked to one-dimensional wave equations. Then we will move on and we are going to investigate the wave equation in higher dimensions. The physical example will be the sound waves. That's a three-dimensional configuration. And then we will also study plane waves and cylindrical and spherical geometries, sound waves in cylindrical and spherical geometries. Then we will move on to a quite interesting topic. We are going to study the so-called water waves. This is the physical example of a nice piece of mathematics. Here the idea is that we will study the wave equation, but we will transform this wave equation into a time-independent equation, and we are going to supply this equation by time-dependent boundary conditions, and this is how we will model the propagation of surface waves. In this section we will also study wave dispersion. I will define later on what this is. This is a very important piece of mathematics. We will introduce also group velocity and phase velocity. These are all words from physics, but I'm going to show you what is the mathematics behind and how you can generalize these ideas. And finally, at the end, I think we are going to study something what you haven't seen before. The physical example will be the traffic waves or the traffic flow problem. We are going to model in a very simple one-dimensional highway how the dynamics of evolution of car density will evolve as function of time, and this we will model with an interesting mathematics, the method of separation, the method of characteristics. That, I think, is a very nice piece of mathematics. Then the course will be finished by a 2-hour exam somewhere in January, although I'm not exactly sure how the exam will happen given the circumstances. Right. So one thing is to have a lecture, and another thing is to really get into the subject if you are interested in this topic deeper. And I'm going to give you here a few references. The first one is a book by Knobel. It's a very thin book. It's called the Introduction to the Mathematical Theory of Waves. I follow this book basically. I don't get commission recommending this book, but I would really advise that you can probably download it from various places. Another and a little bit deeper and more physical insight is given by Billingham and King, the wave motion. It's a textbook in the Cambridge Applied Maths series, and if you would be a student in Cambridge, this is a book what you most likely would be recommended to follow. If you are a bit tougher in maths and you really like mathematics, applied mathematics, I would highly recommend the book by Vidam. It's a bit harder as well, it's a bit thicker, it's also not very cheap, but I think there are some interestingly downloadable copies, I'm not saying more, on the internet. The title of the book is Linear and Nonlinear Waves. Excuse me, Linear and Nonlinear Waves, and this is a very nice piece of mathematics. Then, if you are more physically inclined, I would recommend to download, to get a copy of Sir James Lighthill's Waves in Fluids books. This is more physics-based, but the concepts are very, very nicely outlined. Right, so these are the books. This is how you can help yourself to get deeper into the course, but of course there is another possibility as well. I don't know how this virus situation will develop, but usually I recommend that you can help each other. Of course you can also help each other not just by having face-to-face meetings, but you can also do it via online, maybe discussion forums using Zoom, Google Meet, or whatever ways you contact your friends. You can solve together exercises if you wish. So to help each other, I really mean it. You know, we are all different. Some of us is better, some of us are maybe not so strong, and then or we have different expertise, and we can help each other. Now, what you need for this book, for this course, skills from year 1. Basically, you really need to be familiar with differential equations and integration. I will have no time to explain how to solve a second-order linear ordinary differential equation. I will assume that you know this already. The lecturing style will be kind of mixed. I have all the lecture notes on Blackboard. I will also upload the videos, the necessary videos as we progress on Blackboard. And you can take notes by listening these videos, or you can also look at the online overheads. There will be no handouts associated with this course. Here I have devised a sort of course, how the course will be developed, a kind of timetable. The idea here is that from time to time I would like that you hand in homeworks. The homeworks are not compulsory in a sense that you will not get marks what counts towards the exams, but it will give you a nice feedback how much you really understand. So on the left hand side you see the week, in the middle you see the time of the lecture when I will release the video. Actually I will always release the video a little bit earlier, and in the third column you see the timetable, how I'm going to set the homeworks and when the hand-in time is. Now the hand-in will be on Blackboard, and then we will mark, and then you will get it back with some written feedback. Not a lot, but with some feedback. And then also, of course, in the last column I also recommend to you more kind of exercises. You will get some, you can download the text sheets from the course website. That's also available on the Blackboard. So you can download these exercise sheets, and then you can solve according to this timetable, these various exercises, question 1, 2, 3, etc. You are going to have 5 exercise sheets on Blackboard. So that's my plan. I try to stick to this. I hope I can stick to this, but if there will be changes, I will update this plan depending on how we progress. So that's all. I hope that you will enjoy this course, and if you have got questions later on, you can contact me most likely either via Blackboard or by email. Thank you very much, and I'm going to set up soon, I'm going to upload soon the first kind of get a taste video, why to study waves. I will give you a little bit of natural examples, and after that we will get into the maths. So see you soon. Thank you. Bye bye.